We're going to start looking at motion along a line. And the problems that you see the AP use are generally about a particle moving along a line, but we like to spice things up a little bit. So we're going to use a ferocious calculus beast that moves along a line. And for today, it'll be the Nautilus. Now, we'll start with a position function that tells you the position of the beast on the number line at any time t. And if you're going to talk about position, you have to have a starting point for reference. So a natural spot for us is to use the x and the y-axis as our lines and to use the origin as the reference point. So when we have a position function, it's going to tell us where on the number line is our beast at time t, and when we give it a t value, it will give us a position on the number line. And those positions are going to be the normal things we think of when we think of a number line. So a position of time, or a position of 2, would mean 2 units to the right of the origin, whereas a position of -1 would be 1 unit to the left of the origin. So positive positions are to the right, negative positions are to the left of the origin, and if we're talking about vertical motion, then positive positions will be above the origin, and negative positions will be below. That's an important distinction for us because if you do physics, or AP physics, you may not define things this way, so it's a little bit different. Now, the position function can have basically 3 different notations. Okay, if you're talking about position in general, we like to use S of t. Okay, so position. In physics, you call it displacement. Either one's acceptable, and you'll see both used from time to time. If you're specifically talking about horizontal motion, then a lot of times x of t is used because it makes sense to think of my position on the x-axis would be x of t. And if I'm talking about specifically vertical motion, then y of t would sometimes be used. So you'll see all 3 used, and just understand they all mean the same thing. They're all positions. Okay, now the derivative of each of those position functions, it has a special name for us in the physics world. We call it velocity. So whether it's s prime of t, or x prime of t, or y prime of t, they all give us a velocity function. Now, what does it tell us about the motion of the beast? Okay, so let's review real quick the increase-decrease test. So we took a function's derivative. We called our function most of the time f. And if f primed was more than 0, then that told us something about f. Okay, it told us that f increased. And on the other hand, if the derivative of f was less than 0, then f decreased. And if f primed happened to be equal to 0, then f was not changing, f was constant. Okay, f had a horizontal tangent line. Okay, so f has no change. So we're going to translate those 3 ideas into the physics world here. Okay, so what happens if v of t, which is the same as s primed or x primed or y primed, is greater than 0? Okay, well, if v of t is greater than 0, then your displacement or your position function is going to increase. Now, what does it mean to increase in this context? Let's go back to our page with the number lines here. Okay, if my position is going to increase, that means the numbers are going to get larger. Okay, so if I'm on a horizontal number line, that means I have to be moving to the right because my numbers are getting larger. If I'm on a vertical number line, then my numbers getting bigger would mean I am moving upward. Okay, so in this context, if the velocity is positive, s of t increases, which means the beast moves in a positive direction. So I'll say right or up, depending on which type of motion problem we're doing. Okay, and we can translate that to velocity being negative. So if velocity is negative, what happens? Our position or our displacement decreases. Okay, which means my position on the number line gets smaller. The numbers get smaller, so the beast will be traveling left or down. And if the velocity happens to be 0, then your position's not changing. And so in physics, we say the beast is at rest. So S of t has no change, comma, the beast rests, stands still, even if it's momentarily. Okay, before we move on, let's talk quickly about units. Okay, if S of t is measured in meters, for example, or feet or inches, it doesn't matter, any kind of units, and we'll say t is measured in seconds, then what would the units be for velocity? Okay, well, since velocities are rates, velocity is like a slope, so it would make sense that velocity is measured in this case, meters per second. We think of the velocity as the slope of the position. Okay, now the second derivative of position, which would be the first derivative of velocity, also has a special name in the physics world, and it has a lot of connections to our world that we experience every day, and we call that acceleration. So acceleration is the second derivative of position or the first derivative of velocity. Okay, what does it tell us? Well, it's similar to what velocity told you about position. It told you when position increased or decreased. So A of t will tell you whether or not velocity is increasing or decreasing. So if the acceleration is positive, then that means that velocity is increasing. If acceleration is negative, velocity decreases. And if acceleration is 0, then your velocity remains unchanged. Okay, you might think of this, acceleration equal to 0, is when your car is in cruise control on the highway. Your velocity is not changing, so you have no acceleration. Okay, what about units? Okay, so let's go back and say, okay, my velocity on the previous slide was measured in meters per second. Okay, and acceleration is the derivative of velocity, so I'd be doing meters per second over seconds. Okay, and this is where that strange symbol comes from. So acceleration would be measured in meters per second, right? Which a lot of times is written as meters per second squared, okay, because of our fraction to fraction rules. A lot of times they ask for the units in these type of problems, not always, so be prepared if they do. Okay, so we're given that the position of a beast, an object, a particle, is S of t equals t cubed minus 6t squared plus 9t. For this problem, it's going to be horizontal motion. Okay, so I could have used x of t instead. First step, find v of 3 and find a of 3. So v of t, we need the v function first, is the same as the first derivative of s. And it's a good idea a lot of times to write this out so that your reader knows you know what you're doing. So we get 3t squared minus 12t plus 9. And let's get the a of t function right while we have a chance. So that's going to be the derivative of velocity. Okay, again, it's good to establish that connection. What do we get? We get 9t minus 12. Okay, now v of 3, that's the velocity at time 3. That's going to be 27 minus 36, which is negative 9 plus another 9 is 0. So we stumbled upon a time when the velocity happens to be 0. Okay. What's the acceleration there? A of 3 is going to be 27 minus 12, so 15. Now, determine when the particle is moving to the right. Okay, that happens when the position is increasing, which means that's when the velocity is more than 0. So we take our velocity function, and we want to solve this inequality. This is no different than when they asked you, when is f increasing? Okay, we took the derivative, and we made a sign chart for it. Looked where it was positive. All right, let's factor out a 3, so we can make a sign chart. Figure out when this thing's equal to 0, so we know what to put on the sign chart. And I think this factors nicely. T minus 1, t minus 3. I want to know when that's more than 0, so we make a sign chart. Since we weren't given any restrictions, we can go past 0 if we want. So we have 1 and 3 on the sign chart. This is a sign chart for what? Velocity, label it. Okay. Positive numbers bigger than 3, like 10, will give us a positive velocity. A number like 2 would give us a negative velocity, and numbers less than 1, like 0, will give us positive velocity. So the particle moves right on intervals where the velocity is positive, left on intervals where the velocity is negative. Okay, so since we didn't have any restrictions here, we'll say negative infinity to 1 and 3 to infinity. A lot of times the domain gets restricted because you think of t being time, but that doesn't always have to be the case. Okay, draw a diagram to represent the motion of the particle for the interval 0 to 5. So here's your restricted domain. Okay, so we are definitely starting at time 0. And the number line now represents the x value on the number line where the particle is. Okay, this is not the t-axis, so we have to be careful what we're doing here. All right, so this is where is the particle. T will be an invisible parameter that we can talk about. So let's start off. Where is the particle at time 0? Okay, so what is s of 0? Okay, well, we go to our position function, and 0 gives you 0. So at the origin is where we begin. Okay, so here's 0, and that's also when time is 0. That's not always going to be the case. The particle could start really anywhere we want on the number line. All right, what happens first? We go back to our sign chart. For the first 1 second or the first 1 unit of time, the beast is moving to the right. Okay, so let's mark off where is the beast at 1 unit of time, whether that's a second, a minute, an hour, doesn't matter. We get 1 minus 6 plus 9, so it's 10 minus 6, 4. Okay, so we're at 4 now. This is at time equals 1, and so far this is what's happened. We started here, and the beast traveled in this direction for the first 1 second and landed at time equals 4. Okay, so that's a little diagram of what happened so far. Okay, we go back. What happens next? The beast travels to the left until time equals 3. So where does it head to? Well, let's find out. S of 3 will tell us where it is, which is 27 minus 54 plus another 27, which is 0. So it turns around and it heads back to the origin. So from here we go back to the left. And here we are. Now what's the time when this happens, right? It's at time equals 3. So let me put a little t equals 3 up here above it so I know. All right, and then we go back to the right, and this thing says stop the clock when t is 5. So we're going to move back to the right, a certain number of units. Let's find out how far. S of 5 will tell me that. So what is S of 5? Well, we get 125 minus 6 times 25, that's 150, plus 45. So this is negative 25 plus 45, which is 20. So beast turns around, heads back to the right, and we'll ignore the scale on my chart here. Okay, and we'll just pretend that right here is 20 units. And above that, I'm going to write that happens when t equals 5. Okay, now with this chart, we can answer this question, right? Find the total distance traveled during the time interval of 0 to 5. Okay, now this is different than how much did the displacement change. Okay, in other words, where did I start versus where did I finish? That answer is 20. I started at 0, I ended at 20. That's 20 units, but that's not how far we traveled because we actually went forward and backwards. So I can clearly see from this chart that I went 4 units to the right, 4 units back. That's 8 plus another 20, so the answer is 28. Now, how do you arrive at this answer of 28 without the chart? Okay, well, here's what I would need to do. I need to know where the particle changed direction, and I need to calculate the change in position on each of these intervals. Okay, so for example, for the first 1 second, the particle moved to the right. So if I calculate the position at time 1 minus the position at time 0, that will tell me how far the object displaced, and if I put absolute value bars around it, it'll make it positive, which makes it distance. Okay, the next interval was from time equals 1 to time equals 3. So if I take the displacement at time 3 minus the displacement at time 1, that'll give me how much it displaced, in this case to the left. So this is a negative number, but I put absolute value bars around it to make it positive. It becomes distance. And then the last interval is from, oops, wrong way, sorry, from 3 to 5, because we stopped the clock when time was 5. So if I take where the particle ended up at 5 minus where it started at 3 and put absolute value bars around it, that'll make it a distance. Okay, and this will give me the total distance traveled. Okay, so whether you want to do it this way or with a diagram is up to you. This is a common question, though, in physics type problems that you see. Okay, now I'd like to show you a GeoGebra diagram that simulates this motion of this beast on this time interval and see if what we said on paper matches up with what actually happens. Okay, so on this GeoGebra file here, this blue dot represents the beast. And remember, it started at the origin at time 0, and this slider bar is going to animate and run from time 0 to time 5. And we should notice that the object obeys the motion that we observed. So what was that? For the first second, it travels to the right until it gets to 4. It then turns around and heads back towards the origin, and at time 3, it should be back at the origin. Okay, so the clock's going a little bit slow, but just to go along with my speech pattern here, it should work. So here we go, back to the origin by time 3, and then it should head back to the right, and it should stop at 20 on the number line when t is 5. Okay, so it's got to get there by 5, and it's starting to speed up, and you can see it's about to hit 20. It made it. Okay, so the simulation backs up what we did on paper.